In this problem, we have again a question of solving for the equilibrium concentrations of each species in an equilibrium. We are given starting concentrations, and we should check to make sure that those are not also equilibrium concentrations. So we'll solve for Q. We solve for Q, not K, because we don't know if the concentrations are equilibrium or not. Of course, if Q is equal to K, then we have our answer. So we put in the concentrations that were given for each of the products and each of the reactants. These are already in moles per liter, so we can just leave them like that. We punch these numbers into our calculator and we get a value which we want to compare with K. K has been given as 7.2 times 10 to the 2, so this number is smaller than K. The shift, therefore, to reach equilibrium in this system will be to form more products, and this will cost reactants. This will cause Q to go up until it's equal to K. So how much of a shift is the next question? So now we want to solve in a numerical way for the equilibrium concentrations. We start by writing out our equilibrium again, and we're going to set up an IREC table, an IREC table. In this table, we need all of our amounts to be in moles, except for the last line, which we convert back to concentrations. So we need to solve for moles of each product and each reactant. The moles of V3+ are first of all solved, and of course the container is a 5-liter container. Given the molarity, we now have the right number of moles. This is also, by the way, the number of moles of chromium 2+. Next we need to do is solve for the moles of a V2+. That's at a different molarity, but it's in the same 5-liter container. This gives us a number of moles of V2+, which is also equal to the moles of Cr3+, chromium 3+. Now we can take these amounts and fill in the initial line on our IREC table, knowing these initial amounts in moles. From our calculation of Q, we know that we're going to have a shift to products, and so that shift we can just quantify as X for the moment. So plus X for each product, an additional amount of product, and minus X for each reactant. Reactant will be removed or depleted. So now at equilibrium, we keep X in the equation, so 0.05 minus X for each of the reactants, and 0.75 plus X for each of the products. Finally, so as not to forget, we put these quantities, which are in moles, divide by the volume of the container to remind ourselves that when we use our equilibrium expression, the expression for K, we must switch back to molarity. Well, now we have an equilibrium concentration and equilibrium molarity for each reactant and each product, but we have an unknown in there, and that is X. So we need an equation to solve for X, and the equation is going to come from the equilibrium expression, so the expression for K. At equilibrium, K will be equal to those equilibrium concentrations, the concentrations of products divided by the concentrations of reactants. We put our numbers in there next, and this will give us, with the value of K, this will give us an equation to solve for X. But it's looking an awful lot like a quadratic, and we've seen those. We can solve the quadratic, and you could solve the quadratic from here. There would be nothing wrong with that. It's a bit tedious, that's all. But in this case, if you're sharp-eyed, you see that there is going to be a shortcut. So you look at the equation, how can we remove what is otherwise an inevitable X squared to appear in the equation? And the trick is going to be to take the square root of each side, because if we take the square root of that equilibrium expression, we will remove the x squared. We also have to take the square root of the k value, of course. But the square root of the right side of the equation would simply be 0.75 plus x divided by 5 liters divided by 0.05 minus x divided by 5 liters. And even the 5 liters cancel out. So we're looking pretty good. We're going to take the square root of k for that. And then it's a very simple matter to solve for x. And x, remember, is a quantity in moles. Don't get mixed up with moles and moles per liter. X is the number of moles of each reactant that are lost, and the number of moles of each product that are gained. So now we can solve for the concentration of V3+, the first reactant, simply by putting the actual x value and when you punch those numbers into your calculator, you get a molarity now, because this is moles divided by that volume, a molarity of Cr2+. Now for the products. So we can now calculate the molarity of V2+. We're going to do the same thing. We're going to substitute in the value for x that we have now found, this time into the expression for the equilibrium concentration of the products. So V2 plus molarity, we put these numbers into our calculator, and we get a molarity that's also equal to the molarity of Cr3+. Now you want to check you've done everything right. You want to be able to go home and have a good sleep. You can always calculate Q. Q being equal to concentration of products over concentration of reactants. Whoops, that's not the concentration of products we have there. Let's get that correct. So the concentration of each product is the same, so therefore we can square that term. Concentration of each reactant is the same, so we can square that term, and when we use our calculator we get a value for Q equal to 7.2 times 10 to the 2. This is also the value of K. So we have successfully calculated equilibrium concentrations.